All right, everybody, welcome back. So the last couple of classes we looked at working with parabolas that were in vertex form, and now we're going to take a look at how we might actually apply that to using them to build models of things that occur in the real world. So the first example we've got here says the following function gives the height in meters, h of t, of a batted baseball as a function of time, t in seconds, since the ball was hit. Where h of t is equal to -5 times t minus 2 squared plus 21. And we need to graph the function, and then they have a bunch of questions about it. So you may or may not realize this, but anytime something flies through the air, it actually flies through the air following this lovely parabolic arc. If you don't believe me, go chuck something out the window and have a good look at it. I'll wait. And then so in this case, we're looking at just the height of the baseball. And so similarly, as a baseball flies up in the air and comes back down, the rate that it climbs and then falls again can be modeled by a parabola. So this is actually fairly accurate. We'll see a little bit later that we could be a little bit more precise, but this is not bad for as far as models go. Since it's in vertex form, we should be able to sketch a little picture of this parabola right off the go. First thing we're going to identify is where the vertex is. I can see here that I've got a -2, t minus 2, so that means I'm going to shift my parabola two steps to the right, and then plus 21 here means I'm going to shift up 21 spaces. So my vertex is going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Look at that, 21. I finally got it right. Perfect. Okay, so my vertex is going to be way up here at 21 is my vertex. Now, you might also notice from the function that I've got an a value up front that is not 1. So it's negative, which means it's going to be inverted. And there's a 5 there, which means it's going to be it's going to be stretched out vertically, or it's going to be squished, compressed by a factor of 5. So when I do my usual pattern of over 1, down 1, over 2, down 4, I'm going to have to increase that by a factor of 5. So I'm actually going to go over 1 and down 5. 1, 2, 3, 4, 5. And then over 2 and down 20. Because 2 squared is 4, and 4 times 5 is 20. So I'm going to go all the way down here to 20 spaces down, which is going to be all the way down there. And I'll do it on the other side of the arm too. It's going to be symmetrical. So over 1, down 5, over 2, down 20. And I can start to see my parabola taking shape. And I'm going to do my best to kind of draw it as a curve, although it is a really steep curve. It's going to be hard to get it quite right. Something like that. Okay, it's not the best, but it's not bad. So there's my kind of rough idea of my parabola. And these points that I've drawn here I think are going to be helpful in answering the questions. So the first question is, what is the maximum height of the ball? Now remember that this is not just y. Normally we think of this axis here as y and this axis here as x, and that's still true, but in this case these have actual meanings. On the y-axis, this is telling me h of t. This is telling me the height of the ball. So the y-axis is the height. And the x-axis in this case is t, time. The x-axis represents time. So the first question there says, what is the maximum height of the ball? The maximum height of the ball happens when this function is at a maximum, at its highest point. And you can see that happens right up here at its maximum point. So the maximum height of the ball is going to be 21 meters. That's the highest point it reaches. What was the height of the ball when it was hit? Well, the ball was hit, I guess, when time was 0, because this models the motion of the ball after it was hit. So at time equal to 0, I can go along my x-axis, and time equal to 0 is when x is 0, which is my y-intercept. My y-intercept here, I can actually read off, this occurs here at 0, 1. So what does that mean? Well, that means at time 0, the ball was 1 meter off the ground. So what height was the ball hit at? It was hit at a height of 1 meter. Okay, how long did it take to reach its maximum height? So again, we already know the maximum height happens here at the vertex. But how long did it take to get there? Well, I know the vertex happens at 221. 21 is the height at the maximum height. 2 is the time it got to get there. So the time it took to get to its maximum height is going to be 2 seconds. And then it says approximately approximately how many seconds after it was hit did the ball hit the ground. So basically, how long is it airborne for? And it says approximately, and we'll see why here. You can see as the ball goes up this side and then comes back down the other side here, where it hits the ball is right here. Where the ball hits the ground is right there, because my height would be 0, and I'm assuming that's where the ground is. And so I can only really give an approximation for now. Later on we'll learn some tools where you can be a little bit more exact. But for now, looking at this graph, I can say that it looks like it happens just after this point right here. And a reminder that that point happened at 4:1. So it looks like it's just a little bit more than 4 seconds. So I might say just after 4 seconds. And then the last question here is find the height of the ball 1 second after it was hit. How high was the ball 1 second after it was hit? Well, this point right here represents the point 1, and what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The point 116. And so 1 being the time, 16 being the height. So how high was it? It was 16 meters in the air 1 second after it was hit. Okay, so hopefully that gives you a sense of how if we can model something like the motion of a ball with a parabola, then we can actually use it to pull a bunch of information directly off that graph. That graph is going to actually mean something in the real world. Another example we'll take a look at here. It doesn't have anything to do with motion, but we've got another parabola. And so let's talk about the Hubble Space Telescope. So I don't know if you've heard of the Hubble Space Telescope, but it's been working for a number of years, taking some amazing photos of the universe, of the galaxy. And so the Hubble Space Telescope is able to focus light on distant stars and galaxies. And it does this not with a lens like you might think of, like a big magnifying glass. It actually doesn't do it that way. It actually has this huge parabolic mirror. It's this huge parabolic mirror. You can actually see it in the picture here. It's much bigger than the scientists that are working on it. This huge parabolic mirror basically just catches light that comes in, and because it's a parabola, it focuses it perfectly at one point, and then they can collect that information and make images from it. So it says here the mirror is 2.4 meters across and has a depth of 0.1 meter. So it's quite wide, but really sort of shallow. Just kind of scooches down like this, only about 10 centimeters, and it's almost 2.5 meters across. So we're going to draw a function that describes a parabolic mirror and determine an equation that describes it. So remember that when we say determine an equation that describes it, we're working in vertex form, so we're going to put it in the y equals a times x minus p squared plus q form. That's the format we want to get this equation into. So if the mirror is 2.4 meters across, it has a depth of 0.1 meters, and it's a parabola, then the easiest place for me to place my parabola would be to put the vertex right here at the origin. So I'm just going to place my vertex right there at 0, 0. And then if it's 2.4 meters across, then that means it's going to go 1.2 meters this way and 1.2 meters this way. So it's going to go all the way across this way and all the way across this way. Now you can see here that if I use my grid as one box being 1 meter, it's going to be a very hard parabola to draw. So I'm actually going to treat each box as 0.1 of a meter. So 1, 2, 3, 4, 5. This would be like 0.5, and then 1, 2, 3, 4, 5. There's 1.0, and so on. And I'll do this going the other way. This is 0.5, 1, 2, 3, 4, 5. I'm not gonna write in every single number. That would just be exhausting and not really worth my time. So the parabola is 1.2 meters across. So there's 1.2. I can locate that right there, and there's 1.2. But it has a depth of 0.1 meters. So it only goes up here to 0.1 meters. So that's the depth of it. And so you can imagine if this parabola starts at the vertex and curves upwards this way, then I would have a point right here and a point right here that my vertex has to meet, and so, or that my parabola has to meet. So I could, and again, this is going to be a really hard one to draw for the opposite reason of the last one. The last one was super steep, and this one's super shallow. And you can see I've done a pretty not great job, but you know what? Oh, that other side looked better. Okay, I like the left, but I don't like the right. The point is that's a parabola, and it has this shape. And so I need now to come up with a vertex form of that equation that's going to describe that. Well, I did myself a favor by putting my my vertex right at 0, 0, because that's going to simplify this immensely. This whole equation, if p is 0 and q is 0, just becomes y equals ax squared. So that's a lot easier right off the hop. The question becomes, how am I going to solve for a? Well, if I'm going to solve for a, I need some other piece of information. I know the vertex, I've used that already. If I put in 0 and 0 for x and y, then it doesn't really help me out. It just says 0 equals 0, and that's not very good. But I do know another bit of information, which is this point right here. I know that this point is located at 1.2, pardon me. It's located at 1.2, comma 0.1. And because I know the location of that point, I can now feed that information back into the equation here and solve for a. So I can substitute in 0.1 for y, and I can substitute in 1.2 for x. And then I can solve for a. So a will be 0.1 divided by 1.2 squared. And I'll need to use a calculator for that. But if I put that into my calculator, 0.1 divided by 1.2 squared, I get 0.0694. And it kind of goes on, but I'm gonna cut it off right there. So that's my value for a. And so my final answer is y is equal to 0.0694x squared. And that's the equation that describes it. That's actually not a big surprise because you can see it's a really, really flattened out parabola. And we know that as that a value gets smaller, that's what happens to our parabola. Okay, so that's it for word problems.